Hello, welcome back to this class, Thermodynamics. In our previous discussion, we talked about the specific heat and the molar heat capacities of a matter. Remember that we defined the amount of heat to be just the product of the mass, the specific heat capacity of the substance, and the change in temperature, which is also equal to the number of moles, the heat capacity of the substance, and its change in temperature. We know that we can simplify this one because we know that the mass of a substance is just the product of the number of moles of that substance and its molar mass. We know that the kinetic energy of an ideal gas in any confined volume is just 3/2 of the product of how many particles or molecules are there times the gas constant R and of course its temperature. Remember that the molar heat capacity, even in our high school knowledge, we know that the heat capacity is just the measure of how much heat is required for a specific type of substance or matter is required to change its temperature. We can deduce that for material with high heat capacity would require greater amount of heat to change its temperature, and the low heat capacity material or matter would require lesser amount of heat to change its temperature. And in this topic, we'll be focusing our discussion on the heat capacities of gases and solids. In our discussion of an ideal gas, its kinetic energy specifically, the only requirement for an ideal gas to have a change in its kinetic energy would be a change in its temperature. The change in kinetic energy of an ideal monatomic gas would just be dependent on the change of its temperature. Again, we have this equation about the change of kinetic energy of an ideal gas, ideal monatomic gas, which is just 3/2 nR, the change of its temperature. Now let us consider an sum or a collection of monatomic ideal gas confined in a specific fixed volume, meaning at any given time the volume will remain the same. Now, if we are to introduce some amount of heat into this system or sum of monatomic ideal gas, we know that it will contribute to a change in its kinetic energy. And because of the change in temperature, if this change in temperature is enough to cause a change in kinetic energy, we know that the motion of the atoms or molecules inside this fixed volume would be at higher speeds, and the vibrations would be more prevalent. There will be more vibrations at higher temperatures. And we know that the change in kinetic energy is just dependent on the amount of heat introduced into our ideal gas, into our confined ideal gas. Then from our expression of the amount of heat is just product of how many molecules are there and the specific heat capacity of that kind of molecule or of that kind of substance, and of course the change in its temperature. And in this case, we know that the change in kinetic energy is just equal to the amount of heat introduced into the system. And this amount of heat would result to a change in the kinetic energy of the system. Again, there is no other factor that contributes to the change in the state of the collection of atoms inside this container. Therefore, the only factor that would contribute to the change in its kinetic energy is just the amount of heat being introduced into the system. From this equation, we can directly see that if we are to cancel the common factors on the left and the right side of our equations, we can find a relationship between the specific heat capacity and the amount of heat being introduced into the system. Therefore, at this situation, where we assume that there is a fixed volume of our container, and the same, there is no change in the number of atoms involved, then we can have a relationship that the heat capacity of this kind of substance at at fixed volume is just equal to 3/2 R. This is for the ideal monatomic gas. So its heat capacity is clearly dependent only on the translational kinetic energy of this monatomic ideal gas. Now, if we are to consider the rotational motion of the diatomic gas, which involves motion in both translational and rotational manner. Remember that we encountered this 3/2 R and 5/2 R factor in our discussion of the kinetic molecular theory. And again, for the 3/2 R, this is for the monatomic ideal gas, and the 5/2 R factor is for the diatomic ideal gas. The molecular kinetic theory predicts the heat capacities of most of our common elements. For the monatomic elements, the prediction of the kinetic molecular theory is almost perfect. But as the number of atoms tends to be less accurate in its prediction. So this table presents the common type of gases from the monatomic, diatomic, and the polyatomic gases, and with its corresponding heat capacity. Solid materials, as we know in our basic education, are a construct of molecules or atoms in a manner that they are less likely, that the individual atoms or molecules are less likely to move around freely. This is because of the force of attraction, or the bond between the atoms or molecules involved in the construction or in the creation of this kind of solid material. This structure of the solid material is like a ensemble or a collection of atoms or molecules where they are connected with some potentials. It's like we are looking into a structure of spheres, which represents the molecules or atoms, and the springs are the bond or the attraction or the attractive force between these atoms or molecules. And almost everything we see or observe in nature, not all solids would withstand heat. There is always some point where we can change the figure of a solid material. We can change the behavior, the physical appearance of these solid materials. And at some point, this interaction of the atoms or molecules involved in a specific kind of solids, this is a manifestation of the attractive and the repulsive force, which is naturally occurring because of the interaction of these atoms or molecules. Remember, we have discussed previously that there is always an attractive or repulsive force present if we are to allow two or more atoms or molecules to interact with each other. And because of this attraction, as I have mentioned, we are talking about the potential energy. So these potential energies, which is involved in the interaction of these atoms or molecules. So we can imagine a solid material of like a collection of atoms or molecules attached to each other through a spring. So we have the atom spring system for our solid material. Now, speaking of solids, we are not just considering its kinetic energy. So again, for a monatomic solid, we can have the change in its kinetic energy once we will get the change in its temperature, which is just equal to 3/2 nR delta T. However, we will now consider its potential energy caused by the force of interaction between the molecules. So we can have the potential energy which is just equal to the 3/2 nR change in temperature. Remember, in our mechanics, we know that for the total mechanical energy of a system is just the sum of the kinetic energy, the potential energy, and generally, if there are other factors as the external source of another form of energy. For our situation of our monatomic solid, where we do not consider another external sources of energy, we can just have the sum of this kinetic energy and potential energy, which is just equal to the 3 nR delta T. And since both the kinetic energy and the potential energy changes only upon the introduction of appropriate amount of heat, then we can simply write this change in total mechanical energy to be just equal to the amount of heat being introduced into the system or into the fixed volume material. And this amount of heat which is being introduced into the specific volume of a monatomic solid, this is the same amount, this is just the amount of heat that can be used by the atoms involved to change its kinetic energy and its potential energy. As a whole, this amount of heat Q is just the exact amount of energy that can cause the change in the total mechanical energy of the monatomic solid. We can simply cancel out terms of the left and the right side of our equation. Then we can write the heat capacity of a monatomic solid to be just equal to 3R. And this expression is what we commonly call as the rule of Dulong and Petit. Speaking of this rule of Dulong and Petit, we have the heat capacity of some common solids. We have lead, the aluminum, the silicon, and the diamond. Looking at this graph, the heat capacity of the lead flattens at around 400 Kelvin, and the aluminum flattens at around 600 Kelvin, while the silicon, it flattens at around 1000. And we can see that the diamond, even beyond around 1000, the heat capacity still does not flattens out. So we can see that the heat capacity of a solid, monatomic solid, is less than 3R at lower temperatures, and it approaches 3R at the maximum possible temperature that could change the total mechanical energy of a specific solid. So as we look into the most common solid, at the maximum possible temperature, the heat capacity of most monatomic solid would just be close to 3R. As an example, let us consider this one. We will be solving the heat absorbed by a monatomic solid. We have here a mole of solid lead initially at 326.85 degrees Celsius, which absorbs 10,000 joules of heat. What is the final temperature of the material? This is just an example of calculating the quantity of heat, as we can relate it in your previous discussion in the discussion of the quantity of heat in section 1.5. But here we will just be considering the value of the heat capacity, and we are not looking into the molar heat capacity. remember that in the curve presented in the previous slide, the heat capacity of the lead is approaches 3R at around 400 Kelvin. And here, we are given a temperature more than 400 Kelvin. So, it is safe to assume that the value of the heat capacity at this specific temperature for this lead material is at 3R. So, solving for the quantity of heat, because we are to solve for the final temperature of the object, of the lead sample. So, we know that the amount of heat introduced into the system would just be equal to some factor of its heat capacity times the change in temperature. Therefore, we have this expression where we are given with 3nR change in its temperature. So we can have the expression for the final temperature, which is asked in our sample problem, to be just equal to the sum of the ratio of the amount of heat introduced into the sample divided by 3nR plus its initial temperature. N is the number of mole, and we are given with just a mole of this lead material. So we can just plug in values. Using the SI units, we get the value of its final temperature to be just equal to 1000.9 Kelvin, or that is just equal to 727.8 degree Celsius. So as a wrap up, heat capacity is just a property of a certain gas or solid to absorb certain amount of heat and change its kinetic energy for the gas and the total mechanical energy for a solid material. So that would be all. See you on our next lesson.